I want to thank everybody taking the time off their busy schedule, joining us today. Thank you so much for your time. I hope you enjoyed the presentation and find the information we're presenting useful. Today, we're going to take quite a deep dive into commercial and industrial solar preheat, its application, the sizing, the design of the system, how they're deployed, and we definitely have the benefit of Bob's Danielson insight and experience to, help give us all those good information about these systems, how they're used, and how they're operated. So moving on, just a quick agenda for our presentation today, just for you to have an idea about what we'll be talking about at what point. And during the, we're going to have a Q&A at the very end. And if you have a question, please feel free to write it in the chat section. I'll be more than glad to include it during the discussion, or we can wait until the very end for the Q&A. In either case, that works for us. So moving on, we're going to talk about our energy consumption by sector. As you can see here, transportation obviously uses a tremendous amount of petroleum. That's not really our concern. But when we look at our industrial, residential, and commercial sectors, we see within the past, sort of like 70 years or so, that little green line, the green bar basically within the larger bar, increased a little bit between the industrial. So that's really good news. Industrial is using more and more renewable energy. Same thing we see in the residential and not so much in the commercial realm. Well, we're here to fix that. We're here to provide you with a solution that solar water heating using flat plate collector for preheating can be used toward all these applications. When we look at our commercial and residential buildings, a whopping 8 quadrillion BTU is used for heating alone. So that's a huge opportunity for solar water heating and solar water preheating to be used and deployed.
It's almost the federal budget.
So when we're talking about different solar water heating technologies, we can see them here. We have concentrating solar evacuated tubes. Flat plate collector is what we do and what we're going to be talking about today. Air collectors is another good solution for some areas. They've been used, and then unglazed collector, which are used for lower temperature. As you can see, when we talk about industrial process heat, it encompasses that entire temperature range from 32F all the way to 400. And what we are focusing on today is this up to 170, 180 right here. That's the industrial and commercial preheating is what we're aiming for. And for that application, flat plate collectors are very efficient, very reliable. And that reliability, efficiency, and longevity comes from the design, the simplicity of the design. And we're going to look into more details of the flat plate collectors later in this presentation. But it's really simple. No moving parts means less chance of a mechanical failure in a flat plate collector.
Temperature range is acceptable up to 200 plus. That's technically not super hot. I mean, it's half of 400, so you're running at a nice operational temperature with these systems.
When we're talking about large-scale solar water preheating system using flat plate collectors, the principal components of the system, obviously, they remain the same. You have a collector, there's a storage tank, and there's a secondary auxiliary heating unit acting as backup. We call it the backup, but it should be able to meet the entire load. We'll talk about the details later on, but it's very much similar to what we have behind us here. The storage collector is just supersized with more components and features. So the simplicity of a system that you see on a residential building, that simplicity translates into a commercial building because the main component is still the collector and is supersized and has more components, definitely. Well, what have you seen mostly? Like, what's the major difference when you look at commercial installation compared to residential installation? What are the differences that you see? What are the
Well, the obvious ones are the number of collectors used in a solar, heating mode. There's many more collectors because the hot water demand is there. The demand for that solar energy is there. Primarily, what we see obvious is monitoring of the system. So there's some form of means for the facility managers or even the installers to monitor the system to keep track of it. Because a lot of times some facilities, until they get acquainted with the system, they have no clue what they have on their property. So it's a good idea to have either you as the installer contractor or a third party watching the system. They make monitoring usually includes alarms. They have apps on phones. Mm-hmm. So there's all kinds of ways to monitor them, and that gives the owners a sense of security with the system, especially if they're not familiar with solar hot water, which is very reliable, but it's new to them, so it's something that we want to assuage their fears.
Yeah, give them that peace of mind.
Pumps are larger, piping's larger, all the equipment's larger, racking. There's you can see at the far right multifamily that's I-beam construction, so it's it's heavy. It has to support the number of collectors. On the left you see the columns that were built for that particular system. All that you don't see in residential, that's commercial.
Exactly. And for this type of installation, this type of project, let's say we're looking for our ideal candidate. What would be your ideal candidate? If you have any application that is year-round, that's perfect for solar thermal, because guess what? Sun is usually available year-round. If it's not, you're in big trouble. So, but there are applications and situations that you're sizing the system for a winter load. You need to maintain the temperature inside a warehouse at a certain temperature during the winter time, or you need to melt snow, or whatever it might be, and then that load is not there for the summertime. When this happens, a heat dissipation, a heat sink, so to speak, has to be designed into the system to prevent stagnation overheat problems. But again, the right system, the right solution, that right balancing act, and we get into more details on that, can create a system that can be advantageous throughout the year for both hot months and cold months of the year. One thing that I mentioned earlier that is extremely important is for the auxiliary unit to be sized according to the entire application energy demand. Whatever is your total load for that application, the backup system, the auxiliary unit should be able to meet it.
Correct. Yeah. You don't want to compromise it all with your, I call it the primary heater, but we call it the auxiliary also. You don't want to undersize it. You have 2 weeks of cloudy weather and then tenants, if it's in that mode, or motels or factories, they can't operate. And that does come up with engineers. They design, they're not familiar with it, and so they say, can I undersize my primary? And you have to just no, never.
A lot of people think this is okay. I'm getting another heating system. Can I downsize the primary? Never downsize the primary. The fact that the water is being preheated for your primary is where you save your energy. That's where the energy saving is happening. But the primary has to be there, because no matter if it's a commercial application, residential multifamily application, or industrial application, you never want to run out of that heat, that hot water, that heat energy that you needed. So that is very important. Another factor that will come up is the fuel that you're displacing. So when we look at solar markets globally, the more expensive the fuel, the better ROI systems experience and the more prevalent the markets become.
Usually electric, propane,
fuel oil. These are all, there are areas that don't have access to natural gas, and they have this tremendous heating load still. Solar preheating could be a great application for them. We talked about how we size for the winter and do something with it for the summer. as a heat dissipation. For instance, in case of hotels and motels, especially if they're designing for space heating for the winter time, and that come summer, that load is tremendously smaller. But if that hotel happens to have an indoor pool or a swimming pool, that can be utilized as their heat sink. So they're heating their pool, they're not using their other fuels to heat the pool, and at the same time, they're preventing their collector array from going into stagnation overheat. So it's a win-win situation. In multi-family cases, especially when you have a central system, those are very beneficial. Solar thermal could be very beneficial, especially to the building owner, because the building owners are the ones who are footing the bills, and there's no metering for individual units. They have no idea which unit is using how much hot water. It's usually a flat fee. So if whatever saving they can get, it goes directly basically into their business operation, and as a building owner, it could be very beneficial for them. Here we're going to do a little bit of a case study. This is one of my favorites, and I tell you all why it's a favorite project of mine. It's because it's done on a high-rise building, and there is this misconception that, oh, a high-rise, multifamily high-rise and solar water heating really doesn't go well together. It does. It all boils down to the correct design and correct execution of the design. And once that's done, systems will work seamlessly, and they will have all the benefits and savings that you could see. Here's a project done in 2019, Hawaii, I believe. RM Nakamura was the contractor. And you could see, given the location, sunny location, the energy generation from the collector throughout the year is about, 86,000 kilowatt hour from 50 EC40 collector. So if you take that into account, if you take that square footage into account and the energy generation from that square footage, you will see tremendous potential for solar thermal energy saving. There are other applications for solar preheating. Athletic center, gymnasium, anywhere with multiple showers, different sort of like heating for, they have saunas, steam rooms, all that. They use a tremendous amount of heat. That's a great application. Obviously, restaurants use a lot of hot water, and in some areas they could have space heating also added to that load. Another ready application for a large-scale solar preheating system would be schools. But schools is one of those scenarios that I will let Bob talk about a little, because the design is all that matters, the correct design and then the correct execution. That will make the determination whether this is going to be a successful project or a failure. So,
right, these applications are all good. The two that come to mind as far as little consideration are military bases, and which are usually barracks or living quarters, and then schools. What you have is demand load considerations. So you have to know when they're using all the hot water. I'm not talking about the day, I'm talking about throughout the entire year. If the school is closed or for 3 months out of the year, you have no load. So you have a solar system up there that's essentially doing, I mean, unless the design is correct, it's doing nothing as far as providing heat. There's no load. Same with the military barracks or living space. They could have, 400 occupants for a week or two, and then no occupants or very few for another 2 or 3 weeks. So at those points in time, the sun's still shining, and you need to consider how to deal with the heat. And we all do that. We'll talk a little bit more about that when we get to designs, but that's all addressed in design. We need to know, and we usually, what happens with these projects, we get a set of plans, or architects or engineers or somebody calls us and they say, we need solar thermal. First question is, for what application? Or solar heating, I'm sorry. For what application, they tell us, and then usually there's an amount of solar heat they want from the sun for whatever. We'll discuss that a little further. And then from there, we go and we proceed with the preliminary designs And then they incorporate that into their building on new construction, and then we go, it just proceeds from there. There's a kind of a chain of procedures and that we follow, and hopefully they decide to go solar water heating or solar heating for their building.
Another amazing application is commercial indoor pools, large indoor pools that because what we don't consider is the indoor pool is deprived from the solar energy during the summertime, where the pool naturally gets hot by the sun, and it allows for maybe a couple of months each way. You know, if you're living in a very sunny area and you have an outdoor pool, maybe in March or April, you can start getting in the water without having your heater on because the sun is warming up the pool. Well, an indoor pool doesn't have that. What happens is also these indoor pools are usually within facilities that are air conditioned during the summertime. So the temperature in the room is actually lower than the temperature inside the pool. So the heat is constantly escaping from the pool surface. You're losing a lot of heat, basically.
Right.
So it needs to be constantly heated. So it's not only that during the winter time you need these flat plate collectors, glazed collectors to provide heat for an indoor pool. Come summer, you still have that load to meet. And actually, in cases, it actually goes up a little because during the winter time, you're heating the building as well. So that helps heating the pool within the building. In summer, you're cooling the building itself. Bob talked about military bases. Again, variable occupation, variable load. It's just as long as we know about it, we can definitely make suggestions and make recommendation on possible solutions to be adopted. And so they can still take the full benefits of solar water heating system when the barracks are occupied, and then they won't run into problems when they are not. So we'll talk about that a little bit later. And then to the far right bottom, you have another project that is a favorite of mine, and that's for solar cooling that was done. And this uses our collectors to operate a water-fired absorption chiller. And there are a few manufacturers globally that have these water-fired absorption chillers, and how they work is basically the heat is provided by hot water. So if you have a building that you have a cooling load for the warmer months of the year and a heating load for the colder months of the year, the combination of solar preheating, space heating, radiant floor heating, and then solar preheating for an water-fired absorption chiller could be a year-round solution for basically maintaining the desired temperature and climate within your building, whatever that might be. This could be a large warehouse that needs to be maintained at a certain temperature, production facilities, retail stores, anything that needs large-scale cooling can definitely also take advantage of solar preheated water or water-fired absorption chiller. Another project that Bob pointed out to earlier, the differences that we see in a commercial project. This is Houston, Texas VA Hospital 2018 project, Sunshine plus Solar done the project, and 40 of our EP32s was used to preheat the water for both domestic hot water, and I do believe was also space heating application that they're tapping into for their system. As you can see, the construction is suitable for a commercial application with the I-beams as the base of the structure and our rec track system being installed on top of them. You can also see the columns and how they were rated. There's still more applications that we can tap into with preheated or solar preheated water. Breweries, distilleries, wineries, any bottling facility for that matter. There's a lot of washing, cleaning, sanitation, flushing the systems after each shift or after so many shifts. The heat that used for the pot and distillation itself, boiling water, heating up the mash, all that uses a tremendous amount of heat energy, and solar preheated water could definitely benefit and save a tremendous amount of energy for that. Food production facilities use a lot of hot water during pasteurization, any cleaning that they need to do, any flushing of their systems. Again, we will walk through an example later on that we've done for a meat production facility that they basically use 10,000 gallons of water at nighttime from 11 p.m. to 5 a.m. So that's, when you look at it, it's as good as it gets for solar preheated water to operate, because you have all day, no interruption, to gather as much as sun energy and store it in that solar storage tank and then tap into it at night when you need it the most.
Charge your battery, so to speak.
Exactly.
Hot water, and you use it within 24 hours. That's the optimum with solar heating, is to, as it is with almost all solar, is to use it as you make it, or within a couple of days. Storage it gets expensive, so and there might be real estate issues with where to put storage. So best to use it as you make it.
And we usually size the storage based on more, especially these custom applications that we're talking. We're going to get into more details, but we try our best to optimize the size of the storage, not only the size of the array, but the size of the storage to your load profile, and how much is being used. Other applications include car washes, laundromat. Again, these are no-brainers. A lot of hot water being used on a daily basis. Farming facility, again, a lot of sanitation and cleaning going on. Natural preservation centers. We have in Colorado is one of the most interesting projects that I've seen, the wolf sanctuary in Colorado, because it's located in the middle of nowhere pretty much, and they do not have access to natural gas, and getting propane there is not as easy as you would think in the middle of winter. They have a large solar water preheating system to provide preheated water for both their radiant floor heating and their domestic water heating applications. So we're keeping the wolves warm, which is good.
Wolves need solar.
Yeah, wolves need solar too. This is the High Point Dairy Farms, a 2020 project with 54 TRV32. You see that, again, tremendous energy production from this 1,700 square feet of collector array. So really something to consider, how much roof space you're taking for how much energy generation. And keep in mind, as long as that heat load is there, you will need that energy to meet that load. So let's go with the best solution for the application, so to speak, right? At this point, we're going to get a little bit into some definition, very basic definition, and then basically I'm going to talk about system sizing, system designs, and a little bit more in-depth analysis of how different systems, how they work and how interact with one another. The first definition that I want to point out to is what we call solar fraction. Solar fraction basically refers to the percentage of your energy that comes from your solar water heating system, in our language and in our vocabulary, basically. So if you have a load and 0.7 or 70% of it is coming from solar, you have a 70% solar fraction, and the rest is coming from your auxiliary unit. Keep in mind, the auxiliary unit should still be able to meet that 100% load. Just the solar thermal is constantly preheating the water, feeding it to the auxiliary. So if the auxiliary, for example, is set at 160 and it's already receiving water at 160, it will never turn on. The moment it starts receiving water at lower temperature, solar storage tank is depleted, it's a rainy day, now the auxiliary should be able to come back on and meet that 100% again. Below you see a quick example of analysis that they did for a food processing facility, actually, here in Riverside, California. Close to us, they approached us with a unique problem. Again, a lot of hot water being used at a certain time of the day. Once we did the analysis, the total annual energy consumption came up to 3.7 billion BTU almost. And with 260 TRV40 collectors, they were able to meet in Riverside, California, the performance of the collector changes a bit with the latitude, and the better angle, sun angle, all that comes into play. But on average, anything between 700 to 1100 BTU per square feet of collector is something that we can expect from our collector. And you can see with 260, they were able to meet 70% of their total energy demand for heating, or this much energy basically in a year, 3.7 billion BTUs. This is the interesting part. This is the part that we like, because we get to talk about our preferred, so to speak, preferred methods, and how to arrive to the number of collectors and the suggested system. When we're trying to establish the daily hot water or heat demands, how much energy that application needs on a daily basis, there's several ways of doing it. The most accurate way is definitely using on-site monitoring to measure how much energy is being used on daily basis, on hourly basis, and have that detailed energy load and load profile available so you can design the system accordingly. In absence of that, especially when we're looking with standard loads, such as residential, multifamily, hotels, motels, hospitals, applications like that, there are industry standards that established for many years by ASHRAE, ASPE, IAPMO, and then us here at SunEarth as solar water heating manufacturer with 40 years of experience. We also have our own background and our own information, our own data knowledge that we can tap into to kind of establish at least the estimated daily hot water usage for the standard application. And last but not least, is especially for retrofit projects, if you have an existing heating unit there, it's a boiler, it's a water heater, it's whatever it is, we can meter the fuel that's being consumed. You can look at if it has a dedicated meter, you can look at how much fuel it used, and then use the efficiency of the system to kind of backtrack and reverse engineer your daily loads, basically.
Yeah, most of the industry standards, the center one there for ASHRAE, ASPE, and others, are done and used by engineers for new construction, because there is no daily monitoring. There's no usage that they have for that specific building, so they have to go to the standards. They might vary a little bit depending on the fixtures they're using in the building and what the laundries and whatever else or equipment they're using, whether it's industrial or living spaces. So the initial designs are done with established standards. If the standards aren't there, they try to find something close and try to get their numbers correct, because they have to design the primary system. So once, and then from there we piggyback on them, usually on the initial designs, and then we design the solar based on their numbers. We look at their numbers to check, but usually they're, they don't want to be wrong, because then you have not enough not enough hot water. Retrofit projects, on-site metering, if it's a custom, which most of them are, if we're outside of the standards, ultrasonic metering, which is non-invasive. Devices clamp onto the pipe, similar to the one in the right picture, center picture there, yeah. They clamp on the pipe. They'll give you not only the quantity of water that's used, and that would be measured on the cold supplies to your boilers, but also it'll give you the time. So it gives you a data. It's all recorded on a SD card, and it gives you again, not only quantity, but the time that it's used. So from there, if it's an industrial process and it's done like Amir mentioned in the evening, oh, they use 10,000 gallons at night. All during the day the meter's just poking along, and all of a sudden it's just spinning away, measuring the amount of water and the time. So that's the best, and it's non-invasive. It's usually left on the property for 2 weeks on a normal production work cycle for the facility. And then from there you can determine, how much hot water they use. If they do have meters on their boilers, that's kind of rare, but some do, then you can kind of correlate it with that. That helps the efficiency of the boiler.
Mm-hmm.
And then from those numbers, then we start looking at designing what the facility wants. So those
And
initial
one
numbers.
thing we talk about, when we talk about the standard loads, but I think things are changing. So monitoring, even for a standard multifamily residential, that we have all this ASHRAE, ASFE, IAPMO data, okay, this many units assume this much of gallon of hot water per day. Within the last year, we saw how everything changed. Everybody's working from home. I bet that double bell curve changed a lot for residential, because everybody that was like, people were going to work or school, coming back at night. Now they were all home, working from home, schooling from home, whatever they were doing. So I bet that demand changed a lot. So monitoring will still give you that realistic, especially with things that are constantly changing. Yes, you're right. We might all go back to the offices sooner than later. That might go back, or with the existence of work from home now, the demands might have changed.
Yeah, that's what the monitoring equipment, and in addition to giving you a number to start with, it's monitoring the system once it's built to see that it's working. So as Amir mentioned, and this has come up with a lot of IAPMO webinars, is that the buildings are shut down. What's the solar doing? Well, that's what monitoring will tell you. And if there's something that needs attention, you can act on it.
Exactly. Especially that comes into play more so when you say monitoring, and especially that preventative maintenance part. Keep in mind that with renewable energy technologies, there is a considerable upfront cost, and then the ROI comes into play. So every time something actually an accident happens, that will affect the ROI. The preventative maintenance will help you prevent those accidents that will add an extra. The collector's overheated and I blew these pipes and I need new pipes. Once you know that, you can prevent that from happening in time. Then
Right. One recent monitoring snafu wasn't a snafu in the monitoring. It was a plumber was out at a job and he closed the valve, and so the solar tank was heating up and just sitting there getting hot every day. There was no use because the valve was turned not by the solar people, by someone else, and it was picked up on monitoring. They saw that the solar tank never changed temperatures. It just got hot, stayed hot all day and night, and whoa. So they went out there and sure enough, the valve was changed. So it wasn't the simple things like that can affect, hopefully, if we're fortunate it was caught early, because there's an alarm in that monitoring protocol that says, please check your system and figure out what's wrong. So that's what monitoring is. I would say it's a requirement for large commercial, industrial, solar heating systems.
Here are some of the examples of the standard loads that we're talking about: office buildings, elementary schools, warehouses. Even some of those commercial applications have standard load profiles that we can look into retail and grocery. You see that very large daily hot water demand per patient for the health and basically sector because of all the cleaning and sanitation that's involved in the hospital.
It's a lot more now since COVID too.
Oh, I bet, right. Again, these are some other examples based on ASHRAE standard, based on SunEarth's and industry standards, SunEarth's experience. So these are all for standard loads, as you can see. You can see the applications. It's condominium apartments, hotels, motels, things that have been built so many times that they couldn't arrive to a standard for them. For the custom application, we don't have access to this, so monitoring will play a big role. Once we know how much energy is used, then we use some of our softwares, either our F-chart or our Polyson software, to translate that load to the number of collectors that we'll need. So once that's established, and
Yeah,
then
collectors and storage. So
Storage,
that's
exactly.
kind of your primer for the whole job. So if somebody wants this, the software is very thorough. Gives you percent solar fractions, and if a certain solar fraction is required in a building, then we can, you just input the numbers to obtain that solar fraction, and then the designers and engineers will design the building. Sometimes there's design changes needed. If they need that solar fraction, then they have to kind of move things around, which we've had to help. We help with that. So the PolySun on the right is a more graphic and visual sizing program for people that like to provide that. That's fine. That kind of gives someone an idea of what it's going to look, what it does. Numbers are close, so within 5% of each other, providing you all the data is equal, the same. Both those programs are where we start.
Beautiful. So now we know type of collector. Let's talk about the type of collector that you would need for depending on your application. So earlier we talked about the different type of flat plate collector, glazed versus unglazed. We can kind of see here on the left on that chart the temperatures that they each operate at. As you can see, flat plate collectors can reach much higher temperatures, up to 200 degrees Fahrenheit. For purposes of commercial industrial preheated water, we usually aim at 170 to 180 Fahrenheit temperatures. And here is the major difference, and I'll ask Bob to explain this, but well, why don't you tell me why can glaze reach up to that temperature and unglazed can't?
I'm going to explain it. The glazing is usually glass tempered. It's a heat trap, is what we're creating, similar to a greenhouse. The solar heat comes in from the sun, and comes through the glass, and then it's not able to readily escape. And during that time that it's think of it, it's caught inside there, all of a sudden that energy, that solar energy is absorbed by the absorber that's under the glass, and it's transferred to the fluid, and then eventually for solar hot water usage. So that's where glaze allows you to achieve temperatures, in that range up to about 180, 190. Unglazed, same thing's happening. The solar energy is hitting the glazed collector, and then the fluid is being heated and transferred. The difference is that the outside air temperature is also competing for that heat once it hits the absorber, and so there's thermodynamics. The heat wants to leave before it gets absorbed. So unglazed works in a lower temperature range. For commercial markets, you might think, no, you never use them. But if you use them, like a bottling plant uses hundreds of thousands of gallons of hot water a day, maybe millions, depending on the size of the plant. You can let's say the city water's coming in at 60 or 65. If you can boost it 10 or 15 degrees or 20 degrees, then at those quantities of water, then their boilers don't have to make up as much difference. Also, you have real estate issues, so you maximize the amount of solar energy you collect, and at a lower cost. So when you pencil out which Amir's mentioned, the ROIs, you may see a more favorable ROI with unglazed collectors. Again, that's all specific to the job. Exactly. So that's the main difference between them. They're both good for solar heating, preheating water. It's just the application is where.
I see we had a couple of questions, definitely from Alex. We'll get to that. That's a really interesting question about the agriculture sector. We'll talk about that during the Q&A. And Brian just had a question asking if solar power, which I believe is he's asking for solar electric, and solar preheat can be done with the same equipment. Currently, with our unglazed and glazed flat plate collector, no, because these are solar collectors. There is an alternative application. It's been very much, at this point, it's been experimented on for several times. To the best of my knowledge, I have not seen an established PVT or photovoltaic thermal collector on the market readily available in the US as of right now. We have experimented with it. We still have a lot of work to do on this, but it is a possibility. It's been done. I cannot speak to how successful it was. To the best, I can't, unfortunately, even refer a project that you can look into that was done with the PVT.
It involves obviously even more complexity in the mechanical, and then you add the electrical. There also may be some refrigeration systems incorporated to facilitate extracting the solar heat. So working on them, but they're not
readily available at least.
No, they're not, no.
The next point that we're going to cover is going to be the solar storage, which is, again, as Bob was mentioning, is the battery that you plug into it. It's funny, with on the right, on the unpressurized, you see all those ports on top is like the power plugs ready to be plugged into by a different application extracting heat from that tank. There are, generally speaking, two solutions. The left, you see pressurized solution by A.O. Smith, one of our manufacturing partners. On the right, you see the unpressurized solution by another one of our manufacturing partners, Hydroflex. Both great solutions, depending on the application, they can be deployed. When we're looking at solar preheat, because of the temperatures that we're working with, and unpressurized tank could be ideal because of the cost saving that comes with using it on unpressurized versus a pressurized vessel, which is considerably lower. So that can definitely help reducing the initial cost of the system. In addition, if you're working on a retrofit project and we need to add a large volume solar storage tank, a Hydroflex tank is a great solution because it collapses and it goes through very small openings. So that's another solution for retrofit applications. But generally speaking, 170, 180 degree unpressurized large volume tanks is ideal for our application for preheated water, mainly because first, ease of installation, all that stuff, and then the cost, because if you're looking at 1,000 gallon to anything above more than 400 gallon volumes, the difference between the cost of unpressurized and pressurized storage is huge. So
there's considerations with tanks. You have large volumes, so you have water's heavy, thousands of gallons weigh, you get into multi-tons of weight. All this, if it's a new construction, usually, again, you have engineers involved, civil, structural, mechanical, electrical, all of them are involved. The tank would be, if it's on the ground, would have a footing that's designed for that tank and weight. Or in one particular area, California, seismic, they have to be pretty beefy to support them. With the unpressurized tanks, again, the slabs usually are, if it's a slab that you're pouring, are 6 to 8 inches with rebar, new slabs. If you have an existing location, cities will want to make sure that where you're putting it's going to support the weight that's going to sit there permanently for many years. So you may have to undergo reinforcement of that particular location. Also, with any commercial job, if you're putting any of these tanks in a retrofit situation, you have to make sure they have the proper drainage. That's just kind of something you might forget about. So if there was an issue with any of the plumbing, that there's adequate drainage to protect living spaces, usually, or property. Something to consider. Again, it's designer on the front end. If it's new construction, if it's retrofit, the installer has that all on his shoulders. As long as he has all the boxes checked, he's okay.
Yeah. No. dot all your I's and cross all your T's.
Yeah, but
Make sure everything is being done correctly.
Hydroflex tanks coming up to 5,000 gallons, so they're, very versatile, and down to 200, so they're there's a wide range of those non-pressurized tanks that can be used. Similar to an above ground pool is kind of the analogy. They're insulated. The liner's EPDM, it's resistant to 100 and I think 80 degrees. They store water.
Yeah. Or whatever heat transfer fluid you want to have in your solar storage. It might be depending on the system design, and it's funny, you just arrived to the system design naturally. So we're going to talk a little bit about the common system design and configuration. These are some of the preferred designs, suggested designs by SunEarth. And obviously there are many variations for all these direct, indirect systems. These are just some of them. But in a direct system, our experience and our knowledge basically from the market suggests that we recommend suitable for areas with mild climates, maybe approximately below 25° north latitude. Anything below that will have that mild climate to not have freezes. The reason being is water goes directly to your collector. So there is water in your collector, and if there's freezing temperatures outside, everything will freeze, and of course will have irreversible damage to the entire system. At the same time, because the water is going directly, it's extremely efficient because there is no heat exchanger. As we all know, every time there's a heat exchanger, you will lose some of your efficiency depending on the efficiency of the heat exchanger you use. So it's a great solution, extremely efficient, and we see it in warm climates being used with great success.
Pacific Ocean climates, Caribbean, South America, we do with jobs down in the Central America and some in South America, and they're primarily done with direct. And direct means generally our reference is it's water and it's under some kind of municipal pressure. So it's always full of water. That's what Amir mentioned, that if you have water in the panels and you have freezing temperatures, you don't want those two conditions. You have to, that's the main reason,
main concern
for the upcoming designs that we're going to discuss now.
Yeah, this is now the indirect glycol system, and you will see we have them, with both unpressurized and pressurized solution. The reason why they're called indirect is because your solar loop, whatever it is in the heat transfer fluid that is going through your collector, is separated from the processed water, potable water, whatever sort of from the other side of the system. Basically, there is a heat exchanger. That's why it's an indirect system. In the indirect glycol, how we basically protect the system against possible freezes, especially in the colder climate, is the heat transfer fluid in your solar loop is a mix of propylene glycol and water.
Right, usually 40 to 50%, sometimes 60. We did one above the Arctic Circle and in Alaska, and it was 60%. It was a two-part system. It was 60% glycol, and also it was drain back. So it was a unique design. Again, that's when you get the worksheets and the plans that you. And
you're going a couple of degrees north of the Arctic Circle. You take that into account when you're designing this.
Yeah, you don't want any hiccups.
Yeah, no, definitely not over there. And so again, these systems, because of the design, can be used anywhere. In an indirect glycol system, because the solar loop is pressurized, usually you can use smaller pumps,
right,
to achieve higher lifts. So maybe for like mid-rise to a high-rise solution, this could be something to look into. At the same time, glycol and the stagnation overheat temperatures don't do well together. So proper expansion tank for a steam back solution has to be designed to prevent that glycol to be exposed to over 200° Fahrenheit for too long. At the very last, we get to our preferred method, so to speak, for commercial and industrial application.
It's the top top two, yeah, indirect, because it's all has to do with freezing initially, that, and then indirect drain back, as Amir is going to describe, it allows for overheating concerns and
Exactly.
solutions.
So because overheating is as much as a concern for us as freezes, and people don't think about it as much, but we've put a system, let's say, in Nebraska to provide heat to this large drying facility, for example,
Right.
during the summer, during the winter time. What are you going to do in the middle of summer with that system?
Right. Or,
You know.
or as we mentioned, the
Schools.
schools and the military
Barracks.
barracks. There's
Right.
been.
When we were working on, there was a project in Saudi Arabia we were working on, it was large labor camps for this city that they're building, but because of the temperatures there, it's seasonal work. So they come toward the end of summer and they work toward the end of spring, and they don't work for two because it's just the temperatures there get so hot that it's not feasible for them to do any work. So a drain back solution has the advantage of draining the entire solar loop to a drain back reservoir, or in some cases, with depending on design, if we combine the solar storage and the drain back into one, it drains the entire system once you reach the high limit temperature or the low limit temperature in your collector or your tank. So it prevents the system from freezing or going into stagnation overheat. And for variable loads, this will kind of provide that a peace of mind that the system will not, be stagnating and overheating for too long. Kind of summing it up at the end when you're looking at your project and first approaching it, there are some constraints that you want to be aware of. The first thing is how much room you have for array installation, and by that I mean we need, if you're in the northern hemisphere, we preferably need south facing and unobstructed. So if we have a roof that is north facing and then there's a building behind it, that's not really something that you could utilize. But there are always other solutions. The only caveat is you need to communicate your constraint with us so we can better suggest possible solutions. For instance, we had a case that if they wanted to put the collectors on the roof, the distance between the collectors and the storage tank would have been tremendous. So the engineer went back and forth several times, and then they decided to use a south-facing wall right next to the storage tank to install, I think, 24 TRB-40 collectors to provide heat to two large oil tanks, 10,000 gallon each. So the wall was utilized. So even at the first glance, if you don't see what you need, just communicate that constraint with us, and we will try our best to find the solution to go around that. Second thing is space available for solar storage. That's very important. We need adequate space. And again, something to be aware of. And then if it's an issue, we can always look into different alternative solutions. The primary hot water configuration, for example, in an apartment building, if it's one of those cases that each unit has a separate tankless water heater dedicated to them, it will be difficult to install a central system. There have been cases that each unit got individual collector as railing for their balcony, basically. This is a building in China that each south-facing unit has a 4x10 collector mounted on their balcony. It sort of doubles as a railing, I think, but that's how they did it. But again, you have to be aware of, okay, this is a central system or this is a distributed system. How does it work? What is the project motivation? Is it, for instance, the building owner, the project owner is pursuing LEED points. They want to go for LEED Platinum, LEED Gold, whatever it is. Cases we have Title 24 that they're trying to meet that certain energy demand in Wisconsin, Illinois area. A lot of jurisdictions are now requiring the project to become not LEED certified, but bringing it up to certain LEED standards. So they want you're building this new, for instance, convention center. The municipality wants that convention center to have the points to qualify for a certain LEED certification. So those are the product motivations. Sometimes it's saving, sometimes it's getting away from old technology. We had a project that the engineer's only concern was 2 or 3 old boilers that they were working on, and they needed to have someone with a permit to operate them. The cost of operation was too high, so they were just trying to move away from that. So that was the project motivation. And last but definitely not least is the project budget. How much budget is available? What other incentives are there that can be taken advantage of? For instance, there's a federal tax credit for all these,
Right.
up to 26%. For your entire system installation that can be used to offset that cost. We have this topic is very important because we talked about roof constraint and area available constraint. So a lot of times when I'm talking to engineers and design professionals, because they're not familiar with the system, there could be a miscommunication. They're like, okay, I need 40 collectors. The area of each collector is for 4x10 is 40.9 square feet. 1,600 square feet is the space that I need. The fact remains is you have shading, especially on these commercial and industrial applications, because as you can see, the collectors are tilted. If the collectors are placed too close to one another, and Bob will get into the details about this, they will shade the row behind them. So we want to prevent that from happening. And how we do that is we look at the angle of the sun on December 21st at winter solstice at the lowest point, and we try to place the row behind far enough so not more than 20% of the bottom of the second row will be shaded. And Bob will get into the details of that, but that's the difference between the net collector area and then gross installation area. As a quick rule of thumb, just to have an idea, you can take your net area and time that by 1.2 to 1.75 to get the gross area needed. And that number comes from that 1.2 to 1.75 comes from your latitude. The higher the latitude, the greater the distance. So the larger gross area will be. Bob, could you please elaborate, especially when the area installation is constrained?
Yeah, there's instances where the collectors can be closer together and you have a lower tilt angle, and that's when your demands and load profiles are high almost all year. So in the summer, your load profile is the same, it doesn't change. In which case you can bring the collectors in low and closer together to gain more energy at those points in time. You'll lose some in the winter, but overall you have more collectors up there, so your net is higher, and that's where the sizing programs can help with tilt angle and shading. And we can, you can look at how much shade you get, and then you can take that percentage out of the system numbers, and then it's still you're in the positive.
We call it the balancing act of shading.
Right, like Amir mentioned, there was a system vertical. Well, that's great in the winter. So in the winter time, the sun, especially in northern climates, the sun is low in the sky and it's hitting that panel, close to perpendicular. So in those instances, you'll maximize during that time period your energy, your solar energy gain, and that can help. That all helps. It's not the best, but if there's no room, there's you saw the RBs, the little restaurant there. They have so much mechanical stuff on the roof, exhaust fans, that they put it as an awning outside, and it works very, very nice. And that shows everybody what we're doing too. It's not hidden; it's right out front.
And to kind of sum it off, here is a beautiful, beautiful hotel by the beach. There's, I thought, a good, nice.
That's a cargo ship out in the harbor right now.
Yeah, it's a solar water heating cargo ship that goes around the globe and warms the oceans. No, definitely, this is a hotel by the beach. And as you can see, again, a hotel in a warm climate still has tremendous heating load, and you can see that from the row after row after row of collector being installed to meet the demand from this building. to sum up the benefit that you see from solar preheated using flat plate collector, technology is reliable. It's been around for so long and it's been improved upon over time, but from the very beginning, it was so efficient that it just became more and more efficient with more, some modifications. But the system is reliable. It's been around for so long that been tested in so many different situations and climates, and for sure can deliver those heats up to 180 with minimum problems. It has an enormously high coefficients of performance, and the reason why is you're operating a pump to transfer all that heat. So all that in a residential house, that pump could be as small as a 30-watt pump, which is like light bulb pretty much. In large scale systems, especially, even still considering the amount of energy that's being generated by the collector, you're still running a circulating pump to transfer all that energy, and that's the only energy consumer in your system. So once you put energy generated over energy consumed, you get your COP. It's always 20 plus, and it's always tremendous. Given the simplicity of the design of the flat plate collector and how it's constructed with no moving parts, and if we go with the right design, for the right application, for the right climate, for the right location, the system will have very little maintenance and cost of operation. We had systems that were virtually untouched for like 15, 16 years, and the only time somebody went to check on them was when something went wrong. And this is where what Bob said comes into play, that monitoring is important. But again, that's the case. With that, we're running low a little on time. I'm aware of that. I apologize to everyone. This was a lot of information. I'm going to go right into Q&A, and I know we had a question from Alex early on about what good application do you see for solar thermal in agriculture? I believe any drying process can take advantage of solar preheating water.
Reheating water, some air systems for dehydration,
and we actually
cleaning, processing of fruit.
If you're looking at hydroponic farming and agriculture,
right. Yeah. Plants like to be warm. They don't like too cold, too hot.
Exactly. So those hydroponic systems, we have a case study on them that I'll be more than happy to share with you, Alex. That was solar collectors were used to maintain the temperature in the hydroponic systems. But again, anytime you have a heating load, solar preheated water could be used. And in some cases, as you mentioned, we do have some experience using water-fired absorption chillers to create cold. And you're right, dairies and similar applications have this, that they have a cooling load in the summer and a heating load in the winter. Right. And the combination of these two can definitely benefit them. And Seth is, okay, we have a question from Seth. He wants to know a little bit about balancing the array, this large array. How do you do the balancing?
Well, with commercial industrial systems, you have multiple number of, hundreds of panels sometimes, maybe, 30, 40, 50, or 100, and they're in banks. So we call them banks. Others are in arrays that they're in banks, usually in banks of 8, and then there's a separation, and so it's like a highway. You could get off. You get off at little off ramps, and each off ramp has its bank, and then they all come back into a main trunk line that goes eventually ends up at the storage. So how do you balance it? If you're really good at design, you can balance it with plumbing. So it'd be like a perfectly designed roadway that everything flows right. There's no signals, there's no speed bumps, there's no stopping and starting. Everything is just perfect. Well, that's tough to do. It has been done. Usually it's on systems under 100 collectors that's able to do. Otherwise, when you get into larger systems, there are some design procedures you can use to kind of cut the array in half. In the whole system, you can make it, instead of 200 panels, you can make it an equivalent of 100, using a series parallel design, but to get, even then, you might be very large. They make what's called circuit setters that are available, and that you see that in a lot of commercial jobs where you will not see them in residential generally, small residential jobs. And they monitor and restrict the flow to each bank per your design. So if you need 8 gallons a minute for each bank in your pump, let's say you have 10 banks of 8, so you have 80 gallons a minute you need in your pump. Let's say your pump does 100 GPM at wherever it's going to go to the roof. The restrictors will cut that all down to 8. You'll have 20 extra. If that's the only pump you can get, it'll throttle it. It basically restricts it. You can have, in more more sophisticated designs, you can have variable frequency and variable speed pumps that will throttle themselves automatically. They'll balance the flow. Once they see that they're at 80, they'll just ramp down internally in the motor itself, so in the control system. So all that's available, so you're not, in the end, wasting, you're not using excess energy that just goes, basically converts to heat. But so that's all available. There are designs where you use multiple pumps. It's rare, but that has been done on some pool. I've seen it done on pool systems where instead of one big pump, you have 4 smaller pumps that are going to 4 separate banks, and then they all converge back into the pool. So there's all kinds of different designs. The most common, again, is a circuit setter. It's just it does the job. It's set to a specific flow, and you can leave it there and it doesn't change. Trying to balance it with manual valves is difficult, to say the least. I hope that helps answer the question.
Bob, we have another question from Brian. He wants to know, of course, that's our pleasure. Brian wants to know, what are you seeing the best result, like what's the best basically between parallel and series for the collector? It depends.
Yeah, it depends, of course. Generally we like to say no more than 2 banks in series. Some do 3, and we have our dealers that have done that. In cases where the pumping, they want to minimize the pump energy, and they're to save energy, and then their delta T's change. So as it goes through one, it gets, let's say it bumps 10 degrees and then bumps another 10 and bumps another 10. So when it comes out of the 3 banks of 8, it's 30 degrees higher than when it went in. And so as it's coming back into the storage, all that energy has to be absorbed, either directly into let's say it's a pool, or a Hydroflex storage tank. It's dispersed, and then it makes the round, it makes the trip again, or the heat exchanger. If it is a heat exchanger, the heat exchanger has to be sized large enough to take and absorb that 30-degree difference and put it back into the storage. So that's all in design. We all account for that. The flow, the benefit of series systems is that your pipe sizing is reduced, which is enormous with copper now. You want to make sure you have adequate insulation. Usually you're looking at, in California, 1-inch thick wall insulation. You might, in a lot of cases, use foam insulation or fiberglass, depending on what's required. Underground systems, you might have, like on the hospital, you have a system out there on pylons. Well, the piping's running underground. There are techniques and designs for running the pipe underground, so it's not damaged and it's well insulated. So those are all, again, we're getting into commercial industrial where if you've gone into very sophisticated mechanical systems, everything is insulated. The pumps, everything's covered. It's like you're going out in the Arctic and you're completely covered and all you can see is your eyes through your balaclava. So that's done where energy is their business. And I mean, one I saw was petroleum processing. Everything was, because they sell it. That's their revenue. So if they have heat escaping, to them, that's little dollar bills flying away out of their pocket. So, for them, it's long-term. They're thinking long-term. That's their, design criteria.
And that's something you have to do with solar thermal, given the average life expectancy of solar thermal system is 20 plus years. So you have to think long-term.
Yeah.
You have to think long-term with this system. So unfortunately, I've seen sometimes that quite large system running, and then you're like, oh my God, where is the insulation here? Why is it missing? Why is it not there? And it's just all that money was spent, and then as Bob said, this little dollar signs are just skipping every time that heat goes to waste. So with that being said, anyone else had? I apologize. We went 10 minutes over time. Sorry, we had a lot of information to share. Thank you so much for staying with us the whole time. If you have any more questions, please go ahead and ask us. And you can always reach out to me or Bob directly. Here's our contact information with your questions. If you have anything, thank you, Dale. Thank you guys for joining us. Thank you, Seth. It's awesome having you. I hope you found this information useful. Brian, of course, our pleasure. And please, if you have any more questions, feel free to get back in touch with us.